I'm Sampar Rajabaksha. I'm going to present our paper Improving Vehicle Networks Intrusion Detection using On-Device Transfer Learning. In this work, we propose a novel on-device transfer learning technique to improve one-class classification-based intrusion detection system, which is suitable for deploy in edge devices. First, let me give you a brief introduction and motivation behind this research. Modern automobiles includes around 100 electronic control units to control different functions. Having this much of large number of electronic control units require an in-vehicle network which have real-time data transmission capability with sufficient bandwidth and adequate reliability. Considering these requirements, CAN bus is considered as the most widely used in-vehicle network protocol. However, as mentioned earlier presentation, CAN bus is vulnerable to cyber attacks. In this paper, we only utilize the CAN ID field out of the different fields of the CAN frame. So ID intrusion detection systems have designed to detect attacks on the CAN bus. However, there are some challenges to design intrusion detection systems. The major challenge is the lack of knowledge about the CAN data specification. Other challenges include real-time or near real-time detection requirement given the computational constrained environment and limited attack data availability. One-class classification-based intrusion detection systems have used in the literature to detect wide variety of attacks. These models assume that good representative sample of benign dataset is available to train the models. But it is challenging to collect a dataset to represent all types of benign vehicle behaviors. Therefore, more appropriate way to handle this challenge is to use an incremental learning approach to incrementally learn different benign behaviors using minimum computing resources. We are using such an approach in this paper. So when it comes to the CAN data, CAN IDs are transmitted based on the predefined time interval. This creates a finite set of CAN ID sequences for a fixed window size. Randomness and ID-based priority causes to create large number of CAN ID sequences. This demands to have a large dataset to learn majority of benign sequences. Attacks on the CAN bus, on the other hand, introduce new sequences which cannot observe during benign driving. Therefore, we can utilize this property to identify attacks on the CAN bus. In this research, we propose on-device transfer learning approach to retrain one-class classification-based intrusion detection system. The main idea here is to train the model to predict the center ID given the context from both sides of the center ID. We refer this as pre-context and post-context. Once trained, incorrect prediction can be identified as anomalous frame. First, we train the model offline with sufficiently large benign dataset. Then we deploy this in Raspberry Pi model, Raspberry Pi 4, and retrain only the classification layer using streaming CAN data. Machine learning model includes embedding layer, a data recurrent unit layer, an attention layer, and classification layer. During the retraining, output of the attention layer is used as the input to the classification layer. During retraining, we used optimized data structures such as Python DQ to reduce the retraining time as well. So this is anomaly detection procedure. Since we use a sliding window approach, one anomalous CAN ID introduced few anomalous sequences. Therefore, we consider a small observation window to identify anomalous or benign status. This also helps to minimize the false positive as well. We use two thresholds as anomaly threshold and window thresholds. Since our training method is totally dependent on the benign data, we use benign dataset to estimate these thresholds as well. In here, this figure shows how we estimate the anomaly threshold. We find the minimum softmax probability for each CAN ID as the thresholds. For the window threshold, we select a threshold which gives the minimum false positive for benign dataset. When it comes to the CAN dataset, we use the raw dataset, which is considered as the most realistic attack dataset in the literature. This dataset includes different injection attacks and more sophisticated masquerade attacks versions as well. In terms of the model architecture, our shallow model includes 10,459 trainable parameters, and we only retrain 1,819 parameters during the training, which is the classification layer. These figures show the importance of pre and post context to predict the CAN ID. For an example, in the left-hand side figure, given the 69E125 as the context, it is possible to appear 100 CAN IDs as the next CAN ID. However, as per the right-hand figure, right-hand side figure, given the post context of 2E1354, this reduces to 40. That means context ID sent ID can be predicted with higher certainty given the pre and post context. Therefore, we use pre and post context in our model. This shows the effect of dataset size for model accuracy and retraining. Since our algorithm depends on the benign dataset during the training period, especially for initial model training and also the retraining period, we use next CAN ID prediction accuracy to monitor the model learning progress. In here, figure 9 shows the accuracy and overall F1 score improvement with the dataset size. For the overall F1 score, we consider the average detection capability of attack as there are 7 attacks. This clearly shows that when we increase the dataset size, both center ID prediction and attack detection capability increases. Figure 10 shows the effect of the pre-trained modeling training process. For this one, we selected 2 cases. First, we train the model with a fixed dataset size. This is shown in the blue color. Next, we use another 2 million dataset as the streaming dataset to retrain the old layers and only the classification layer. For an example, if we use only 100,000 as the pre-trained dataset size, it gives around 20% accuracy. Next, considering this as the pre-trained model, retraining all layers with streaming CAN data can achieve around 50% accuracy, whereas retraining the classification layer only achieve around 30% accuracy. These accuracies increases the dataset size. When we use 3 million as the initial dataset size, both old layer and classification layer approximately achieve the same level of accuracy after retraining the streaming dataset. That means if we can train our initial model with a sufficiently large dataset, we can achieve a higher level of accuracy by only retraining the classification layer. That's what we used in this paper. This shows the performance comparison. CAN-CID is the model which we proposed in our previous research. CAN-ODTL is the pre-trained model, and CAN-ODTL is the model which we proposed in this research after retraining the pre-trained model. Based on this, you can see that CAN-CID and CAN-ODTL achieve same level of accuracy, but CAN-ODTL is computationally more efficient than the CAN-CID as a result of using an attention layer with less number of GRU nodes. On the other hand, as expected, pre-trained model shows a higher false positive rate due to the unseen benign frames. This shows the effectiveness of using the retraining over the classification layer. Computational efficiency is another important factor for a CAN IDS. Therefore, we analyze the computational overhead for retraining and inference using Raspberry Pi. CAN on-device translearning retrain around 1,600 CAN frames per second out of 2,500 frames in this dataset. This requires to keep 900 frames in the buffer, which only takes around 75 kilobytes in the memory in the Raspberry Pi. During the retraining, this utilized around 45% of CPU and only 157 megabytes of RAM, given that the 8 GB RAM of the Raspberry Pi model which we used. For the inference, we used 4 models: TensorFlow implementation and TensorFlow light conversion with quantization. That is just to reduce the inference and retraining time. Float 16 quantization achieve the same level of accuracy as original TensorFlow model with 78% model reduction and 83% inference time improvement. We considered 100 millisecond window as our observation window, and it takes around 125 milliseconds to give the prediction. Usually, based on the literature, average driver response time ranges from 0.7 second to 1.5 second. Therefore, our model is capable of detecting these attacks within a small fraction of driver reaction time. And this work shows that the effectiveness of CAN-ODTL to detect wide variety of attack in near real time, especially injection and more sophisticated masquerade attacks. However, it requires to train the initial model with around 1 hour dataset to achieve a higher accuracy through the retraining of the class or through the classification layer retraining. As future work, we are planning to deploy this CAN-ODTL in a real vehicle by connecting Raspberry Pi to the OBD2 port and test it on the real attacks on the proving ground of our industry partner which is Horiba Myra. Thank you.